All right, in this video, I'm going to be looking at solving equations that aren't quadratic in form, but they're equations where we could use quadratic techniques, okay? So first off, here's a true quadratic equation. So let's say we're trying to solve x squared minus 2x minus 15 equals 0, okay? You've done things like this before. You should try to factor. If factoring doesn't work, you go to the quadratic formula, or if you're trying to factor and you're just not getting it to work, you would go to the quadratic formula. So I would try this one out because it's a 1 here. I'm going to try factoring for sure. So x and x. In this spot, I need things to be 15. So I'm going to try either 1 and 15 or 3 and 5. But 3 and 5 would be the most likely thing to give me a 2 there in the middle. So I'm going to use 3 and 5. All right, when I do, I know that I need it to be a negative 2x, so I need the bigger one to be negative. And if the signs are different, I do get the negative in front of the 15. So I was able to get this one factored. I didn't need to go to the quadratic formula. So now I'm going to set them equal to 0. Okay. On this one, I'm going to subtract 3 from both sides. Here, I'm going to add 5 to both sides. And I wind up with x equaling negative 3 or x equaling positive 5. So those are my two solutions. All right, so that one really was a quadratic equation. It was degree 2, so I was able to use the techniques we normally use. Okay, now I'm going to vary this problem a little bit and show you how that same technique can be used on problems that really aren't quadratic, but they're going to wind up having a feel. The solution has a kind of feels like this, okay? So for instance, this is one type of problem I actually did have you do before. What if I had an x to the 4th and an x squared instead of just the x squared and the x? So what if this was to the 4th power and this was to the 2nd? Okay, well, it's really not quadratic because it's to the 4th power. It's a polynomial with a degree of 4. But I'm still going to use quadratic techniques. So I'm going to come in and think to myself, well, you know what? If I put x squared in the first spot in each, I would get an x to the 4th. And then if I used the 3 and the 5 to make the 15 happen, and I made the 5 negative and the 3 positive, that would give me the negative 2x squared in the center. Okay. All right. Now, at this point, I'm thinking, well, I would like to try to factor some more, but 5 is not a perfect square. Okay, this one's not a difference of squares. So like earlier, if you were trying to do this, you would have to just kind of stop at this point almost. But we know more now. So we're able to set x squared plus 3 equal to 0, or x squared minus 5 must equal 0, just like we did earlier when it was just x plus 3 and x minus 5. And even though we can't continue factoring at this point, we can use the square root method. So we can come in and subtract 3 from both sides. Okay, that would give us x squared equals negative 3. Over here, add 5 to both sides. That would give us x squared equals 5. And then what we'd have to do is continue, because your job, when you're being asked to solve, your job is to figure out what x is. So you'd come in and you'd square root both sides. Okay, and there'd be 2 square roots of that number. So x would equal positive or negative the square root of negative 3. So that's when you come over and you think about negative 3 and how it's negative 1 times 3. So if you were doing the square root, you'd want to take the square root of negative 1 times 3. So you can split it up since it's multiplication, and that would be I, and that would remain under the radical, and you'd have an I square root of 3, and that would be the end of that side, okay? All right, so let's kind of recap that. So here was the difference. After you subtracted 3 and got to here, that's kind of like where you were on this one. On the original problem, you were done at that point. This was your solution. But on this one, we still had that squared on the x. So we had to go a little further, and we had to come in and square root both sides. Okay, so we would do the same thing over here. We'd come in and square root both sides, making sure we did both the positive and the negative square root of 5. Okay, so that would give us x equals positive or negative. This one doesn't turn out to be imaginary. This one just turns out to be square root of 5, positive or negative. Okay, so you know how this had a degree of 4? That meant there were going to be 4 solutions. Here they are. I square root of 3, negative I square root of 3, square root of 5, and negative square root of 5. Okay? Right, now like right next to that one, I want to do one kind of like this one. What if I had x plus 1 squared minus 2 times the quantity x plus 1 minus 15 equals 0. Okay, so let's look at this one. Compare it to the one we just did. All right, now it looks kind of weird because where we used to have in the original problem, lower it a little bit so you can see it, where we used to just have an x here, an x being squared, and then an x. Here we have an x plus 1 being squared, and then an x plus 1. Okay. All right, so you could multiply x plus 1 times itself. You could distribute the negative 2 throughout. You could get all of this reworked so it was all multiplied out and ready to either factor or use the quadratic formula. Okay, but I really want you to look at this. What about, see if this makes sense. What about just trying to factor, but instead of just using x right here and x right there, use x plus 1. Wouldn't that give you x plus 1 squared? Okay. All right, and then on the 15, we'll do like we did before. We'll use a 3 and a 5, and we'll make the 5 negative and the 3 positive. All right, do you see how when you do the inside 2, you would get 3 times the quantity x plus 1. The outside 2 would be negative 5 times the quantity x plus 1. So you'd wind up with that same middle term. And you see how the negative and the positive multiplied together gives you the negative. So this step right here has been correctly factored. Okay. So what you can do at this point is say, well, you know what then? What I really have is x plus 4. See how I did the 1 plus 3? Over here, I could do the 1 minus 5 and get x minus 4. I could set those equal to 0. And I would get my 2 answers, one of them being x is negative 4 and one of them being x is 4. So here's my 2 answers. Okay. So do you see how the original problem, nice and simple, straightforward question that we had way up here at the beginning, I just varied it here and here a little bit. So on this one, we needed to use x squared instead of just an x. And over here, we could use an x plus 1 instead of just an x. But it turned out to be approached in the same way. Okay. All right, I want to look at the one I just did and show you the variation you'll see in my math lab, or the approach you'll see there. And maybe this will make more sense to you. Sometimes the way you approach this, they use something called a U substitution. Now, they may not call it that in an early algebra class, but that's the idea. Where the x plus 1 is, you let u or some other variable stand for the x plus 1. Then you rewrite that equation. So this might click for you. You rewrite that equation using u everywhere you saw the x plus 1. Then you forget about that for a minute and you go in and you do your factoring. You with me? So you just make that substitution. Everywhere there is an x plus 1, that's where I'm going to be putting a u. Then I'm just going to work with that simpler looking equation for a minute. Then I can set each one of those equal to 0. And I get what I saw earlier, u equaling negative 3 or a variable equaling 5. The thing is, what we're being asked to solve over here, was an equation with an x in it. So if you use this approach right here, you have to remember, you have to think about what you did earlier. You have to get x back in. So where u is, I'm going to put an x plus 1 back in. Where the u is, I'm going to put in the x plus 1 again. Okay? So when I do that, I wind up with seeing how x equals -4 or x equals 4. So these two approaches for the same problem you can do. What you'll see a lot of times them showing you how to do in the textbook would be this side right here, because it's a very powerful technique. It's a way of simplifying the look of the equation so that you don't bog down in how complicated the equation here looks. You just make it look nice and simple and you work it using your old technique. The hard part is to remember this down here at the end, to remember to go back and put the x plus 1 back in, because your job was to solve for x. Okay. All right. So I want to look at two more examples. So these two problems right here, okay, would have been called quadratic in form. Okay. It wasn't really quadratic, but it was quadratic in form. Okay. All right, now let's take a look at two problems that kind of give you some insights into more that we're going to do later. We can take a problem like this, or one like this. And what we're going to find is after I do the initial couple of steps, these are going to turn out to be pretty much like that really easy problem we did at the beginning. Okay, so this equation right here is really rational. That means fractional, has variables in the denominator. This one is a radical equation. Okay, so I want you to see that we can clear the fractions on this one by coming in and looking at how, if we multiplied by x squared, how that would get rid of the denominators. And if I cleared the fraction by multiplying by x squared, that's okay to do as long as I multiply all the way through on both sides. Okay, because I've kept it balanced by multiplying through on both sides. If I do that, watch what happens. This term becomes x squared. This term, do you see how on top we have the x times x? When we knock out one of those x's, we're going to have a 2x. Here, we have x squared on the bottom, we have x squared on the top. So won't that cancel out, leaving me just minus 15? Then if I do 0 times x squared, I'm going to get 0. Okay. So what we just did is we transformed the original equation into the one that I started the whole thing with. Same thing happens over here with this radical equation. Right. See that square root where we have an x trapped underneath the square root? If we're going to solve for x, we need to get that x out of there. And so what we're going to do is use something similar to, really similar to what I did over here when I was getting rid of the squared. By square rooting, I'm just going to do the opposite. I'm going to get rid of the square root by squaring. So I'm doing that, undoing the square root, so that over here I get 2x plus 15, 2x plus 15, and then I'll square the left side as well. Now, you will need to make a mental note on this one to check your answers, because you might get what they call an extra solution. These two equations aren't exactly equivalent. The one on the bottom might have a solution that works there that doesn't work in the original. So just make a note when you're doing this type, you must check. And the same thing's true over here. You must check for a slightly different reason. This problem, these aren't quite equivalent either, okay? Because the original question here had denominators, okay? So there's spots where you might have an issue of division by 0, so you have to watch out for that. So just make a note on both of these to just check and make sure on the rational one that you don't get a denominator of 0, and on the radical one, just make sure that the number actually works when you plug it in. All right, but notice on this one on the right, if I subtracted the 2x from both sides and subtracted the 15, there we are, right back to the problem we had at the start. Okay, so neither one of these was quadratic. They weren't even what you would call quadratic in form, but they're rational or radical equations that after you do a step or two, you've turned them into a quadratic. And so you're able to now come in and do the factoring and set the factors equal to 0 and get your solutions. And it would be exactly the same process as what we did earlier. Okay, so you would do the same thing here. You would take the time to factor. And of course, if this were a brand new problem, it would take us a little more time. We wouldn't be going so fast, but we've already done this several times. So I'm kind of rushing through that part. So you get to here, but here's the thing. You must check. And what you're checking for here really is in the original problem, check if the denominator equals 0 when you plug these in. So when you go to your original equation, see how x would have to be equal to 0 in order to have a problem? Like if x were 0, you would have division by 0, and that would be an issue. Okay, so on this one, x better not be 0, otherwise you would get division by 0. And since this wasn't x equals 0 and this wasn't x equals 0, these should be okay. Okay, now I still could have made an arithmetic mistake, but what I'm saying is if all of your work, kind of assuming that all this work was correct, you still have to check to make sure that the numbers you got don't wind up causing a problem here. Don't wind up making that denominator 0, okay? All right, and then on this one, you need to check to make sure you don't have what we call an extraneous solution. So you got to take that original problem before you squared both sides. Take the original problem and you just check each solution. So what happens if I plug in a -3? This, by the way, makes more sense as you get into more advanced classes and you understand the concept of domain, because that's what the issue really is. That's what you're checking. When you plug in -3, does it really work? And then you're going to take the original equation and you're going to double check that when you plug in 5, oops, let me get back to that. When you plug in a 5, okay, does it really work? Okay, so that's what we're looking for. All right, so let's do that. Let's work them both out. So here, this would be -6 plus 15 under the radical. This would be 9, square root of 9. And the principal square root of 9 is +3 only. It's not -3. So that one actually does not check. So we have to rule that one out. Let's check this one. That would be 10. When we add 15, we get a 25 under the radical. And the positive square root of 25 is 5, and that's what it was supposed to be. It does check. This is the only solution. This right here is called an extraneous solution or root. You'll hear that language. It's a solution to this equation, but not to the original. Okay, so it's not an answer to the original question. You have to rule it out. Now, sometimes both of these work. Sometimes one works and the other doesn't, like it did here. And sometimes neither will work. Okay, so you really do just have to check them. And it's not always the negative one that you rule out. Okay. All right, so let's just recap what I was doing on this page. Let me shrink it up a little bit so you can see more. All right, I was having you look at how a very simple problem like x squared minus 2x minus 15, which you could do in your sleep. Here's the solution to that one. How that same technique can be used to solve one that was really x to the 4th, or one where you had an x plus 1. instead of an x, okay? And then it also can be used to solve rational and radical equations that turn into a quadratic. Sometimes when you do your first step on those, they become quadratic. And when they do, then you already know everything there is to know about solving a quadratic equation. Isn't that neat? Okay. So this is looking at solving equations using quadratic techniques. Okay. I'm going to stop this and get this posted.